Thank you. First, I would like to thank the organizers for inviting me here. It's a great pleasure to be in Paris. And I also want to thank everybody who is here, who already survived 6 talks today and still decided to attend the 7th. Yeah, so all what I'm going to talk about is joint work with Michael Hull. And I'm going to talk about transitivity degrees of countable groups. I will start by reminding some basic definitions. Oops, okay. Yep, it's too much. So during my talk, all groups are going to be countable. So whenever I say a group, I mean a countable group. And omega is going to denote, sorry, I have to learn how to work with this. So omega is going to denote a countable finite or infinite set. Now we say that the action of my group on a set omega is k transitive if omega has at least k points, k elements. And for any pairwise distinct k tuples, a1 and so on ak, and another tuple of pairwise distinct elements b1 and so on bk in omega, there is an element of the group which moves the first tuple to the second tuple. Okay? So if k equals 1, then this is the standard definition of a transitive action. So being one transitive is just transitive. And this is a well-known generalization. Now we define transitivity degree of a group as the supremum of all k such that G admits a k transitive action.
Faithful.
Yes, faithful. So thanks. K transitive, yes, faithful is missing here. It will be missing in a couple other places, but yes. So we only consider faithful actions, right? Well, this notion is very well known in the theory of finite groups. So let me ask some questions just to make sure that everybody is following. So what's the transitivity degree of the symmetric group on n symbols? It's n, right? So the action on, the natural action is already n transitive, and it cannot be more than n transitive, because if you are k transitive, you need at least k factorial elements to be k transitive, right? Because there are k factorial distinct k tuples. So Sn cannot be more than n transitive, and its natural action is already n transitive, so transitivity degree is n. Now, okay, transitivity degree of an is n minus 2. That's very easy to see. Well, if G is a finite group and transitivity degree of this group is at least 6, then it's known, and actually this result uses classification, that G is either an or Sn. It's either the alternating group or the symmetric group. Now, if transitivity degree of your group is 4 or 5, then there are only finitely many such groups, finite groups. Actually, these are finite simple groups, the so-called Matthew groups. So you see that the spectrum of groups or transitivity degrees of groups looks like this. Every group is one transitive. Well, transitivity degree 1, well, every group has transitivity degree at least 1, because the natural action on itself is transitive. Then for groups of transitivity degree 2 and 3, there are lots of them, but these conditions are somewhat restrictive. For groups of transitivity degree 4 and 5, there are only finitely many examples in each degree. And for groups of transitivity degree more than 6, there are exactly 2 examples for each n, and these examples belong to these 2 infinite series, an and Sn. So As you increase the transitivity degree, this condition becomes more and more restrictive, and the more its transitivity degree, the more rigid is the world of groups which have that transitivity degree. So this motivates some natural questions. What happens if you think about infinite groups? And surprisingly, many natural questions are open for infinite groups. So here I'll mention some of the questions which motivated our work. So the first question is, well, for finite groups, for every k, you have a group of transitivity degree exactly k, that's sk, right? Now for infinite groups, well, is it true that for every k you can find an infinite group with transitivity degree, well, exactly, you know, k, right? Well, what?
Take an infinitely iterated root product of symmetric case.
I don't see why transitivity degree is bigger than 1. Remember, the action must be faithful. But, well, let me say what's known here. So for k equals 1, 2, and 3, and infinity, well, for a countable group, transitivity degree can be infinite because the group can admit k transitive action for every k. So for these 4 numbers, the answer is yes. But starting from k equals 4, to the best of our knowledge, it's open. There are some countable groups which have 4 transitive natural, 4 transitive actions. But the point is that you have to make sure, if you want to say that transitivity degree equals k, you have to make sure that there is no other action which is even more transitive, right? And this is somewhat difficult because you need to control all the actions of the same group. So probably that's why the problem is not so easy. Now, when you pass to countable to infinite groups, there is a completely new phenomenon which does not occur in the world of finite groups, and that's the so-called high transitivity. So a group is called highly transitive if there is a single action of that group on some countable set. Now the set will be, of course, infinite, such that this action is k transitive for every k. So then this action is called highly transitive. And again, the action is supposed to be faithful, so the word faithful is missing here. So there is an equivalent characterization of highly transitive groups. A group is highly transitive if and only if its natural embedding into the symmetric group of omega is dense. So symmetric group on a countably infinite set has natural topology of pointwise convergence. You think of every permutation as a map from omega to omega, and omega is just discrete set, say natural numbers with discrete topology. You think you endow this set of permutations with a pointwise convergence, and then the symmetric group becomes a Polish group, Polish topological group. So it's completely metrizable, separable topological group. Now, it's very easy to see that in topological terms, being highly transitive is exactly the same as being, the action is highly transitive if and only if the natural embedding of G in this symmetric group is dense. So G is a dense subgroup. So this allows to use some topological ideas when you work with highly transitive groups. And you will see some applications of these topological ideas later in my talk. So there are a couple questions associated to this new phenomenon. It's clear that if your group is highly transitive, then the transitivity degree of your group is infinite, right? Because there is single action, which is k transitive for every k, so the supremum is infinite. But what about the converse? Now the question asks, suppose you have group with transitivity degree infinity. What it means that there is a series of actions so that these actions are more and more transitive. So for every k, there exists a k transitive action. Does it follow that there exists a single action? Well, I'm talking about faithful actions as usual. Does it follow that there is a single faithful action which is k-transitive for every k? We don't know. And finally, as you can see in the case of finite groups, there is a very nice classification of groups of high transitivity degree. Is it the case for infinite groups? So can we somehow find a reasonable classification of countable groups of high transitivity degree, or maybe at least highly transitive groups as the ultimate case? Well, we don't have answers to all these questions, but we do have some partial progress. So what I'm going to talk about, well, in some natural algebraic and geometric settings, we can answer the first two questions, and we actually show that in some natural algebraic and geometric settings, the first problem, the answer to the first question is no, and actually there is a very strong rigidity phenomenon. So either our groups have transitivity degree 1 or infinity, and having transitivity degree infinity is equivalent to being highly transitive. So this is some sort of rigidity phenomenon in geometric settings. And then about the second problem, well, at least we can find some sort of classification of groups of high transitivity degree. And I will explain in a minute what kind of classification it is. So I will start by discussing some known examples of highly transitive groups. Well, there are obvious examples. So by F sim n, I denote the symmetric group of n, which consists of permutations with finite support. This is a countable group. So F stands for finite. And then there is alternating group, which is a subgroup of F sim. So this is the subgroup which consists of permutations of finite support, so that every permutation acts on its support as an even permutation. Okay? Or you can think of it as a direct union of the natural chain of alternating groups embedded in each other. So, but there are also some, well, with these trivial examples, you can play a little bit, so it's very easy to see that whenever you have a subgroup of a symmetric group which contains a highly transitive subgroup, then this subgroup G is also highly transitive. And then you can play a little bit with this, and this is not a deep result. It's like an easy exercise. The proof is just a few lines, but I think it's nice. So for every finitely generated infinite group Q, you can construct a finitely generated subgroup G inside the symmetric group, such that this group splits as a short exact sequence of this sort. So there are two nice things, because this subgroup sits inside G. G is going to be highly transitive, but also G is finitely generated. So, of course, these groups are not finitely generated, right? But using this proposition, you can construct finitely generated examples of this sort. For example, you can construct finitely generated amenable highly transitive groups. Well, just take Q to be infinite cyclic group. Then every group which splits as an extension of this sort is going to be amenable because it's locally finite bicyclic, so it's amenable, right?
So you take the group generated by left translations and finitely supported permutations, right?
Yeah, right. So you look at the permutations on the Kelly graph, right? Exactly. And
I think not only I think I have seen this, but I think that I read somewhere that this group is known to be never finitely presented. So it sounds.
Yeah,
I think it sounds familiar to me.
Well, this group appears like many times, like at least like a couple of papers in the 90s, maybe.
yeah, I'm sure it's a known construct. I mean, the proof is just 2 lines, so this is not a deep result. It's just an easy observation, which I want to mention as an example. But
Who is who?
he was my student at Vanderbilt, and now he is a postdoc at Chicago, at University of Illinois at Chicago. So again, this is don't think this is some sort of deep result. It's just easy exercise for an undergraduate student, not even for graduate. So, but there are some non-trivial examples. So I think of these examples as sort of trivial, but there are some non-trivial examples. So first non-trivial example is the free group, non-abelian free group. All such groups are highly transitive. It was first proved by MacDonough, and then it was later observed by Dixon that if you look at the symmetric group, the full symmetric group of natural numbers, then in some sense, if you take two generic elements in the sense of the Bayer category theorem, they will generate a dense free subgroup. So this, yeah. So next non-trivial example is free products. So every non-trivial free product, except the infinite dihedral group, is highly transitive. So there are, well, it was also proved that every fundamental group of a hyperbolic surface is highly transitive. Of course, for g equals 1, it's not highly transitive, not even too transitive. That's exercise. Now, non-elementary hyperbolic groups without non-trivial finite normal subgroups. Well, the absence of finite normal subgroups is necessary. The reason is that if you have a group which acts even too transitively on a set, then every non-trivial normal subgroup acts transitively. Now, if your action is highly transitive or even just too transitive, the set must be infinite, right? So the subgroup, the normal subgroup, cannot be finite because it must act transitively. So this is kind of necessary condition, but if you exclude the trivial counterexamples, then hyperbolic groups are highly transitive. And it was proved by Gerian and Glasner that out of n for n at least 4 are highly transitive. Actually, it's interesting that to prove that, they used a very strange, I mean, very non-trivial, I would say, approach. So whenever you prove that something is highly transitive, the question is on which set does this group act. So to prove that out of n is highly transitive, they use the action on k tuples of elements of the free group which project to generators of the so-called Tarski monsters. Those are groups with all subgroups are finite cyclic, and not just any Tarski monsters, but specific Tarski monsters constructed by Olshansky. So it's somewhat not the first thing you would try, right? So then, in a more recent paper, it was proved that every ICC group, well, ICC means infinite conjugacy classes. A group is ICC if every non-trivial conjugacy class has infinitely many elements. Every ICC group with infinitely many n's, in the standard geometric sense, is highly transitive. So now, looking at these examples, what you see that these trivial examples, well, they are all kind of the same sort. And these non-trivial examples, they all have some built-in hyperbolicity inside, right? So you wonder maybe, well, first of all, maybe it's possible to generalize this set of non-trivial examples so that there is a more general class which covers all these examples and where you can make these hyperbolicity assumptions precise. And then maybe you can find a classification. Maybe you can say, well, every highly transitive group is either of this sort or of this sort. And actually, we do both. So first, we generalize all these non-trivial examples, and then we prove a theorem which more or less, well, roughly says that every highly transitive group is either of the first sort or more or less of the second sort, and that's what I'm going to talk about. So to state, first of all, I'm going to state a generalization of these non-trivial results. To talk about this generalization, I'll need a couple of auxiliary definitions. The first one is the definition of an acylindrical action of a group on a metric space. So an isometric action, whenever I say that the group acts on a metric space, I always mean by isometries by default. So isometric action of a group on a metric space is called acylindrical if for every epsilon greater than 0, there exist two constants, r and n, such that for every two elements, for every 2 points in the metric space, if these elements are far away from each other, then the stabilizer, well, the epsilon stabilizer of this pair is finite. So what it means, in general, this action doesn't need to be proper. So the stabilizer of a single point can be huge. But if you take 2 points which are far apart, and you look at elements of your group which move both points just a little bit with an epsilon, then this set is finite. So here is the picture. So you have 2 elements. You can think of r as a big number and epsilon is something small. So then the set of such elements is finite. So, I think this definition goes back to the notion of acylindricity for groups acting on trees, which Zlil introduced a long time ago. And then in this form, it's due to Brian Bowditch. So here are some examples. Oops. Every group acts on a point. The action is acylindrical, just because there are no elements which are far apart, right? There is nothing to check. If G acts on a tree, then the action and the edge stabilizers are finite of uniformly bounded size, then the action is acylindrical. Exercise. Psst. And if you have a proper and co-bounded action, it is necessarily acylindrical. Note, however, that if you just have a proper action, if you remove co-bounded here, properness does not imply acylindricity in general. So, well, there is a counterexample. And the reason is that when you define properness of the action, you just say that something is finite, while acylindricity requires some sort of uniform finiteness. And this is what fails for the general proper actions. Okay. So now, if you have a group which acts on a hyperbolic space, let me just remind you standard definitions. An element is called loxodromic if the orbit map induces a quasi-isometry from the infinite group generated by this element to S. Every loxodromic element fixes exactly 2 points on the boundary of the hyperbolic space, the Gromov boundary. And 2 loxodromic elements are called independent if their fixed points sets are disjoint. So whenever you have a group which acts on a hyperbolic space and contains 2 independent loxodromic elements, you can play the standard ping-pong game and show that the group contains 3 subgroups and it contains infinitely many loxodromic elements and so on. So, well, for acylindrical actions of groups on hyperbolic spaces, there is a nice classification. So again, this is not a very difficult result. It's some sort of natural thing. If G acts acylindrically on a hyperbolic space, then exactly one of the following 3 things happen. Either G is elliptic, which means that all orbits are bounded, or G contains a loxodromic element and is virtually cyclic, or G contains 2, and hence infinitely many, independent loxodromic elements. So in the first 2 cases, the action is called elementary, and the third case is called non-elementary. If you compare this theorem to the general classification of group actions on hyperbolic spaces, which was done by Misha Gromov in his original paper about hyperbolic groups, then you can see that this theorem actually rules out 2 cases, the case of parabolical actions and the case of the so-called quasi-parabolic actions. And also, in addition, it characterizes this situation, which are called, this sort of actions are called linear actions in algebraic terms. Anyway, so in what follows, I'll be interested in non-elementary actions, And if the action is non-acylindrical, then being non-elementary is equivalent to having unbounded orbits and not being virtually cyclic. Okay? So now let's say that a group is acylindrically hyperbolic if it admits a non-elementary acylindrical action on a hyperbolic space. Okay? Strange definition, but it turns out that this is the right definition. So lots of things which are known for hyperbolic and relatively hyperbolic groups can be generalized to this class of acylindrically hyperbolic groups, and the class is quite large. So for example, it contains all non-elementary hyperbolic groups, just because they act properly and co-boundedly on hyperbolic spaces, therefore the actions are cylindrical. It also contains all relatively hyperbolic groups. That's an easy exercise. Well, non-elementary. It contains mapping class groups. That's due to Mazur and Minsky and Bowditch, who proved that the curve complex on which the mapping class group acts is hyperbolic. That's Mazur and Minsky. And then Bowditch showed that the action is acylindrical. For out of n, it's, well, it's a combination of two results. So Bestvina and Fine found an action of out of n on some hyperbolic graph, which is not quite acylindrical. And then with Francois Damani and Vincent Girardel in joint paper, we showed that you can perturb this action somehow to make it acylindrical. Then most free manifold groups are acylindrically hyperbolic. And more precisely, if you take any subgroup of the fundamental group of a compact free manifold, I don't assume that G is finitely generated, otherwise I could just restrict to fundamental groups themselves. So then either G is acylindrically hyperbolic, or it's virtually solvable, or it has a normal subgroup isomorphic to Z. In both cases, virtually solvable groups and groups which have amenable normal subgroups, they cannot be acylindrically hyperbolic, so you have to rule out these cases. But these two cases correspond to small manifolds in some sense. So for example, if G is itself a fundamental group of a compact irreducible manifold, then this case exactly corresponds to the Seifert-Fibert manifold, and these are just small manifolds. And well, groups of deficiency at least 2. A group has deficiency at least 2 if it has a presentation with 2 more generators than relations. And also, if you have a residually finite, finitely presented group with positive first L2 Betti number, then it is acylindrically hyperbolic. So there are lots of, I mean, constructing the space on which the group acts acylindrically, it's not an easy thing, but once the space is constructed, you can do a lot about, I mean, you can prove a lot about this group. Okay, so next, for every acylindrically hyperbolic group, there exists a unique maximal finite normal subgroup, which I'll call finite radical in this talk. In general, of course, such a subgroup may not exist, but if the group is acylindrically hyperbolic, it always exists. It's similar to the case of ordinary hyperbolic groups. And here is the theorem, our first main result with Michael Hull. We show that every acylindrically hyperbolic group with trivial finite radical is highly transitive. So you have to rule out the case of non-trivial finite radical because, as I said, highly transitive groups cannot contain finite normal subgroups. But if you rule out the trivial cases, that's what you get. And this theorem generalizes all the examples which I mentioned. You will see this in a couple minutes. So in particular, if G is acylindrically hyperbolic, then its transitivity degree is either 1 or infinity. If it does have a non-trivial finite normal subgroup, transitivity degree is 1. If it doesn't, it's infinity. And there is a similar result in some geometric settings. For example, if G is a subgroup of a mapping class group of a surface of genus G with P punctures, and you can also allow the surface to have boundary components, the result is then completely the same. Yeah, one thing is missing here. G is infinite. So here, G is infinite subgroup of a mapping class group or an infinite subgroup of a compact 3 manifold group. Then transitivity degree is either 1 or infinity, and the following conditions are equivalent. Transitivity degree is infinite, G is highly transitive, which answers one of the questions which I mentioned at the very beginning in this particular settings. And this also can be characterized by in geometric terms. So these two conditions are actually equivalent to G being acylindrically hyperbolic and having trivial finite radical. Okay.
Denis, can you say a word about the set omega, on which you act?
You can act on natural numbers. Omega is a countable set without any structure. Right, I'll say on the next slide, I can. So the idea is fairly straightforward. So every transitive action is an action on some coset space, right? So you want to define a subgroup so that the action on the corresponding coset space is highly transitive. And the idea is this. So you want for any k cosets, for any two k tuples of pairwise distinct cosets, you want to have an element in your group such that this element maps first tuple to the second tuple, right? And well, this is equivalent to these elements being in H. So you can just add all such elements for all tuples. The problem, however, is that if you do this in a careless way, what you get most likely is you get the subgroup, which is the whole group. So then the action is the action on the point, which is trivial. So you have to choose these elements carefully, and it can be done. So there are two key ingredients. That's the notion of a small subgroup and the notion of small constellation theory in acylindrically hyperbolic groups, which we use to show that you can you can add such elements to H in an inductive way, so that at each step your subgroup H is small compared to the big group. And here is the exact definition of being small, but it doesn't really matter. And so that you can continue the procedure, and then you just do the standard inductive thing. And what we use small constellation theory to choose elements so that the subgroup remains small at each step. So this is rather technical, so I don't want to go into real details. What I said here is kind of straightforward and trivial approach, but non-trivial details are hidden. Okay, just to remind you, here are examples of highly transitive groups which we discussed so far. So examples from 1 to 6, all these non-trivial examples are particular cases of our theorem, because all these groups are acylindrically hyperbolic with trivial finite radical. And also we have some new results. For example, in their paper about out Fn, Garion and Glasner asked, what about out F3? Well, out F2 is out of question because it has finite normal subgroup. What about out F3? They could not prove that out F3 is highly transitive using their methods. We did it. And also for mapping class groups, that was another question from the paper of Garion and Glasner. So we answered that question as well. For G equals 2, it is not highly transitive for the same reason. There is this hyperelliptic involution, which is in the center of the mapping class group of a surface of genus 2. So you can only hope for this group to be highly transitive starting from G equals 3. And also, among other new results, are one-relator groups with at least 3 generators. There are some other new results. Now, I want to say a few words. About pressing the wrong button. Okay, so now the second main result which we prove, it somehow shows that all the groups which are highly transitive are either of this type, like kind of obvious type, or they have some sort of freeness built in. So to make this precise, I need another definition, which is the definition of a mixed identity in a group. And here is the definition. So everybody knows what an identity is, or at least you've heard that in the talk by Alexander Alshansky. A mixed identity is an identity with coefficients. So a mixed identity of a group is an element of the free product of my group and free cyclic group, infinite cyclic group generated by X. So here is my notation for such a word, such that W of G, where W of G is the result of substituting an element G from the group G inside this word instead of X. So W of G equals 1 for all G in G. Okay? So this is like an equation in my group, and we say that my group satisfies a non-trivial mixed identity if it satisfies a non-trivial equation. If the whole group is the solution of a non-trivial equation, where an equation is non-trivial if this element is not the trivial element of the free product. Here are some examples of groups which satisfy non-trivial mixed identities. If G is a direct product, you fix one element from the first multiples, one element from the second multiple, then it's easy to see that G will satisfy this non-trivial identity. So the first commutator will only have non-trivial B component, the second commutator will only have non-trivial A component. They commute. So similarly, it's an easy exercise. If G contains an element A with conjugacy class of size n, so if G has a finite conjugacy class, then it satisfies this mixed identity. It should be X instead of G, but it doesn't matter. And if A is a non-trivial element, then it's a non-trivial mixed identity. There are some other examples. For example, a symmetric group, the full symmetric group satisfies this mixed identity where A, B, and C are these involutions exercise. It's the same sort of idea can be used to show that Thompson's group F satisfies a non-trivial mixed identity. And of course, neither of these examples satisfy the real identity. Well, I mean, the first two examples can in principle, but they don't need to. And last two examples, they don't satisfy any true identities. So being a group which does not satisfy any mixed identity is a very restrictive condition. I call such groups MIF groups, mixed identity free. So MIF is abbreviation for that. And you can also prove, and that's an easy observation, again, there is nothing deep here, that G is mixed identity free if from the model theoretic point of view, it resembles a free product. So precisely if you look at the universal theory of G with coefficients from G, then it's the same for the group G and for every free product of this sort of a group and a free group of rank n for every n. So for those who are familiar with elementary theories, that should be clear. For those who are not, I'll probably just...
No restriction on n?
No, if it's true for one n, it's true for any n. So that's equivalent.
So for cyclic group,
yeah, for example, you can take infinite cyclic group instead of Fn. Well, here are some properties of mixed identity free groups which follow actually from the previous slide. Mixed identity free groups are directly indecomposable. They are ICC, infinite conjugacy classes. In particular, they have trivial centers. They have infinite girth, which is some geometric property which I don't want to talk about now. Non-trivial normal subgroups of a MIF group is a MIF group. So the class is closed undertaking normal subgroups and so on. There are some other properties. So it's a rather restrictive condition. Now here is the main theorem, which the second main theorem which we prove, which shows, which captures the difference between trivial and non-trivial examples of highly transitive groups. So suppose G is a countable highly transitive group. Then exactly one of the following two conditions holds. The first condition is that G contains the alternating group as a normal subgroup, which makes it a trivial example. Or G is mixed identity free, which, just to remind you, from the model theoretic point of view, means that G resembles a free product. Okay? So let me say a few words about the proof of this. It's rather topological. So you think of G as a dense subgroup of the symmetric group. Remember that if you have a highly transitive group, it's a dense subgroup in the symmetric group, right? we consider two cases. So first case, if G contains a non-trivial permutation with finite support, then we show that the whole alternating group is already there. And this is the first case. But the second case, if G doesn't contain a non-trivial permutation with finite support, if all permutations, all non-trivial elements of G have infinite supports, then we show that for a generic element S in the symmetric group, generic in the sense of the Bayer category theorem, the subgroup generated by G and that element is the free product, naturally. But then, suppose that G is not mixed identity free, which means that it satisfies a non-trivial mixed identity, but G is a dense subgroup in the symmetric group. And the set of solutions of every equation in a topological group is always closed. All right? So if you have a dense subgroup which satisfies some equation inside symmetric group, then the whole symmetric group satisfies this equation. But that cannot happen because W of S is not equal to 1. That's because of this isomorphism. That's a contradiction. So in the second case, you get that G is mixed identity free. So from this theorem, for example, you can get some results even about acylindrically hyperbolic groups, because acylindrically hyperbolic groups, they cannot be of the first sort. That's, well, for example, it follows from the fact that every acylindrically hyperbolic group has finite amenable radical. It cannot contain this locally finite group as a normal subgroup.
I'm very skeptical about this isomorphism that G and S generate a free product, because like the density implies that you can take S and you can move it by conjugation with the disjoint support, and they have to commute. So in the group generated by G and S,
no, it's not. No. The topology only sees finite things. So you can make S arbitrarily close to being disjoint, but it will never be really disjoint. Think about it.
is S an element with like finite support or with infinite support?
No, S is an element with an infinite support. S is an generic, yes. Generic will have infinite support. So, well, it's actually written in the archive. The paper is in the archive, so you can check it. If you look at acylindrically hyperbolic groups with trivial finite radical, then what you get from this theorem that every such a group is mixed identity free, which says something about its elementary theory, universal theory, because, as I said, it cannot be of the first type, therefore it's of the second type. Okay, and finally I want to conclude with the picture which geometrically shows all the results which I mentioned and some other results which I didn't mention. So here is the class of acylindrically hyperbolic groups with trivial finite radical. Every such a group is highly transitive. That's the content of our first theorem. Then the class of all highly transitive groups is divided into two categories. It's either mixed identity free or contains alternating group as a normal subgroup. And also, all inclusions which are proper on this diagram are indeed proper. We have results which show that. So I want to stop now.
Yeah. How do you prove this result that if you have a countable subgroup which avoids finite permutations and you have a Z free factor?
Well, basically the idea is the one suggested by Martin, but Martin was trying to push it in the wrong direction. So,
Where is Martin?
Kasabov. Well, somehow you show that for any finite set of elements of your group, you can find an element in the symmetric group which does not have short relations with these elements. And here you use some sort of local arguments. And then you use the Bayer category theorem to make it work. So it's not, I mean, it's not a trivial proof, but it's not too complicated. You have to work with permutations a little bit, and there is one hands-on part in this proof, but that's as much as I can say in a few seconds. But I can explain the proof if you want later.
So, did the definition of acylindrical and hyperbolic groups come out of this problem of studying high transitivity?
No, the definition was motivated by some geometric applications, and that's something which we were working with François Damani and then San Girardel, and they have several papers about that.
Also, do you know other problems where hyperbolicity comes up, or you think you can make a statement with acylindrical and hyperbolic?
Yes, there are a lot of them. So I have a paper in the archive that was titled Acylindrically Hyperbolic Groups, and there is a short survey in the end of this paper which surveys some of applications of this sort. So you can just look at the paper, or we can talk after this after this talk, because I mean there are lots of such things.
Do you know the transitivity degree of free Burnside group?
Free Burnside group? Good question. Well, first observation, so yeah, we discussed this with Alexander Alshansky, and the first observation, it cannot be highly transitive, because it satisfies a law. If you have a dense subgroup in the symmetric group which satisfies a law, then the whole symmetric group must satisfy the same law, but it doesn't, right? So it's not highly transitive. And there are some restrictions. For example, if the exponent is odd, then transitivity degree is 1. That's easy to see. And if the exponent is even, well, you know, it's some finite number. What is precisely the number, I don't know.
I wanted to ask this related question. Can you strengthen this mixed identity free to have more than one variable?
Yes, if it's mixed identity free with respect to one variable, then it's mixed identity free with respect to any set of variables, and that's very easy. There is such a lemma in our paper which proves exactly this.
Well, this is part of this theorem that like you can add big free group to the elementary theorem. This is equivalent.
Yeah, it's part of that theory, but it's a very elementary fact. I mean, if you think about it a little bit, you will see the proof.
In fact, Robin has questions, Tatiana has. Let me.
Okay, so for the acylindrically hyperbolic groups with trivial finite radical, so does your construction actually show, in a sense, that a generic subgroup of infinite index setting gives you a...
Yes, you can formalize it this way.
So it's generic?
Well, you have to be a little bit careful, but yes, there is a genericity model. We don't include this in our paper, but there is a genericity model in which this is exactly the case.
Do you know anything about groups with degree of transitivity 1?
Every group is at least one transitive, but well, there are some obvious obstacles. For example, well, if your group has non-trivial finite normal subgroup, as I said, or say non-trivial center, then its transitivity degree is 1, and so on. So, I mean, there are some easy algebraic conditions which imply transitivity degree 1, but in general, this is the most general class of groups. So there are more groups of transitivity degree 1 than of any other transitivity degree. So starting from 2, transitivity degree becomes more and more restrictive.
Dima has a question.
What is transitivity degree of the Grigorchuk group? Right? I don't know.
So just a quick question. So I asked about the acylindrical transitive action of Aldefine. So in your paper with Girardel and Damani, do you use the first construction of hyperbolic spaces for the spin and train?
Yes.
And if so, whether is it known whether the action on factor graph or factor complex or...
No, it's not known if it's acylindrical. Still, there is no natural space on which out of n acts acylindrically. You have to do one of my constructions or our constructions with François and Son. It could be, yes. On the free factor, it could be, but it's known to be WPD if you know what it means. But that's somewhat weaker condition which requires acylindricity along axis of loxodromic elements, but not globally.
Is it correct that acylindrically hyperbolic group has free normal subgroup?
Yes. That was the content of the message which I sent to you.
No, I just verified that.
Yes. Has free normal subgroup.
So all these examples
Yes.
fits into
Yeah.
the situation.
Yeah.
It's free normal subgroup.
Yes.
Okay, then I think we can ask all the speakers this afternoon.